Yeah, thank you for the nice introduction, and I'm happy to see that many people still here at this late time. Today I'm going to talk not about cold band glass, but about the chemical toughening of glass. Probably everyone has heard of chemical toughened glass. I just call it CTG from now on, but it isn't really used in a wide range in the building industries. And the reason for this is because inherent in the process of toughening the glass chemically, there are pretty big variances on the variations on the pre-stress level and on the distribution of the pre-stress. So now I'm going to show you what we thought of in Aachen and how we tackled the problem to give the engineer a method to know the strength of his material. Here's a short outline of my presentation. First, I'm going to tell you about the possibilities of toughened glass and compare it to the thermal toughened version, which we all know. Later, I will introduce the used method of photoelasticity measurement and explain which device we used and why we had to choose this one. The experimental analysis will then conclude our experiments and show the results of the photoelastic measurements. In the end, I will sum it all up and give a little outlook on what to do next. Yeah. Without further ado, I will start with the theoretical background. Okay. There are today two main principles in the toughening of glass. I said the first one, thermal pre-stress. There the residual stresses are induced by a heating process. The glass is heated up to 640 degrees, and then it is cooled down rapidly using air jets. Due to the different cooling time of the outer and inner layer, the residual stresses form. Here you can see such a curve. On the outside there's a compression zone which reaches with thermal toughened glass up to 20% of the glass thickness, and in the middle there are the tensile stresses. Here is the chemically toughened glass shown. It is achieved by a chemical alteration of the glass composition on the outside. And we already can pinpoint some major differences. For the compression level is nearly twice as high as with thermal toughened glass. But we also can see that the depth of the compression zone is much smaller, which imposes us with quite some difficulties, especially in the use in building construction. I will tell you a little bit more about the pros and cons. The pros of CTG are their higher flexural strength and also impact strength, and it is workable in its pre-stressed state. So far with thermally toughened glass, we weren't able to polish the edges or drill holes in it after we had the pre-stressing. It also yields a high optical quality, so we have no iridescences due to the rollers of the furnace. And the flatness also isn't impaired because the whole sheet lays in a bath and doesn't need those rollers. But where there's light, there's also shadow. So here the cons pose the user with really high costs at the moment, and the formerly said the variation in strength values. And this is where our journey starts. We wanted to know how big is this variation, and when we produce such a glass sheet, can we measure how high the actual pre-stress state is? So to understand the pre-stressing, we have to look close on the glass, actually so close that we see the atoms. Here you can see the sodium atoms, the hydrogen and the oxygen atoms, like in a normal soda lime float glass. And it is now immersed into a molten bath of potassium ions. Those are the K+ ions here. And what happens now is, due to diffusion, the hot glass tries to reduce the concentration gradient, and some sodium ions solve into the molten bath. Now we, with the spaces left open by the sodium, the potassium ions tend to bind to the oxygen, and as you can see, the potassium ions are bigger than the sodium ions, and therefore a compression zone established, and the little flaws are pushed together, and so our bending strength is raised. And what is the result of this process? A glass with the properties of a glass that is far more resilient to crack growth, because crack growth only occurs when the surface stress surpasses the impressed residual stress. We, as said, have also a high optical quality, and the stress distribution, as seen on the plane there on the right, is pretty even. So you don't have, due to air jets or something blowing the cold air, you get a pretty even distribution. Yeah, but still unknown is the depth and the absolute value of stress. And to overcome this uncertainty, we needed an easy applicable measurement method to see inside the glass. This procedure then was found in the scattered light measurement with the SCALP 05. It is a photoelastic measurement method, and I'm going to explain it to you right now. The measurement is non-destructive, so it could be easily applied into a production line. And it employs the Tyndall effect, which describes how light behaves in mediums that are under stress. The light gets scattered, so a laser penetrates into the surface, and then the light is scattered on the glass atoms, and a camera measures the amount of scattered light. So we get those nice formulas where we can see delta, which is the optical path difference, and it is the integral of the stresses over the way of the laser inside of the glass. The unknown constant for us was the C, which is the photoelastic constant, and we had to find a way how to determine this. And especially with chemically toughened glass, we had to use a device with special properties. Those are shown here. The predecessor of the SCALP 05 worked with an entry angle of the laser of 45 degrees. And as you can see, it penetrates the glass pane quite fast. So with this, you can measure deeper. But what we wanted to know was the stress distribution on the first micrometers, where the CTG is pre-stressed. So we had to choose. So there's the laser. We had to choose the SCALP 05 with an entry angle of 80 degrees. And as you can see, the laser is quite long in the first micrometers, and although we only have a maximum measurement depth of 2.45 millimeters, which isn't ideal for thicker glasses, we now have a 4 times higher information density on the first micrometers. And this is the part that is the most interesting, because in the middle of the plane, the tensile stresses remain relatively constant. So this is output of the SCALP 05. We can see the optical path difference and the resulting stresses. And we also can see that the derivation of the optical path difference over the length yields our stresses. And again, there's the optical constant. On the left side, we see TTG, and on the left side, the CTG. How could we now? Right now, we could measure the curve of the pre-stress, but as you have seen before, the C would scale the absolute levels of the stresses. So we had to think of a measurement method of a test setup to determine our C. This will be told in the experimental analysis, where we determine the photoelastic constant for CTG, and then I will show you our measurements and the results of them. C relates the optical delay of the light to the occurring stresses, and therefore has to be known. It is in TTG glasses 2.72, and it is well known so far in the literature, but for CTG it is unknown. Therefore we took this test setup. It's a regular 4-point bending test, oriented a little bit on the DNAN 1288. And what we can achieve with this is a constant bending moment between the both loads. And for the constant bending moment, we can derive stresses, and therefore calculate our C. We had to measure in 2 states. In this formula, you can see, if you remember, the deltas are related to the stress, and they have the index 1 and O, and 1 is after loading, and 2 is before loading. So we put the stresses in relation. This is simply Hooke's law with the E modulus of glass, and the strain was measured also. I will show you exactly how we did it. This is a procedure. First, we affixed and teared the strain gauge on the glass while lying flat, so there were no stresses except the residual stresses, and no influence on dead load. Then it was put on the support, and we measured with SCALP. So we got our optical delays we needed in this formula there for the time 0. The strain was also measured. Then we put on the load, and the stress changed and the strain also, and so over Hooke's law we could rearrange the formula and calculate our C. This C is for CTG determined to 3.03, a little bit higher than for TTG, but now we have all our instruments together to really determine the stress in the chemical toughened glass. This we did on quite some samples. Here they are shown. The investigated specimen had different thicknesses, all with 9 measuring points as shown on the right side, and 5 measurings per point. those 5 measurings per point were both from tin side and from the air side, from the production process of the float glass. So we had totally 90 measurements per specimen. The yielded information is then the compression stresses on surface, so the level, and then the depth of the compression zone, and at last the tensile stresses at the beginning of the curve. They are shown again. So these are our results, and as you can see, as the thickness improves, the compression, surface compression, gets lower. So the fact if it was the tin side or the gas side is not recognizable. Those are, by the way, all means of the points measured. On the other hand, there are the tensile stresses, and here we can see a difference between tin and gas side. It appears that if we measured from the gas side, the tensile stresses in the middle of the pane were higher. For logical reasons, it would have been ideal if they had the same height. But yeah, that's what we found. Maybe the laser is impaired by the tin side, or like atoms coming on the side during the production process. Here we now can see the depth of the zone, and above it you can see again the level, and also the depth was influenced by the side we measured from. And the gas side had a higher strength, which we would explain by the fact that when the glass lays on the tin, maybe some atoms would start diffuse into this, so the chemical structure there is not as good for the single ion exchange with potassium ions. Oh. To sum it all up, the measured surface compression reached up to 270 megapascal, and they decreased with higher thicknesses. The depth was up to 59 micrometer and increased with higher thickness. All the glasses were pre-stressed for the whole time. So if you for the same time, because if you lay the glass into the molten bath, over time the pre-stress gets bigger and reaches a maximum after about 24 hours, I think. And ours just were pre-stressed for 7 hours. Yeah, and the tensile stresses decrease with higher thicknesses, and are on a span from nearly zero, they can never be zero, nearly zero to 2.2 megapascal. Yeah, the summary I will skip because Mr. Lauter is already getting nervous. But the outlook we thought of was why would we just chemically toughen our glasses and have the losses like if the strength, if the impact on the glass surpasses the compression zone, the glass will shatter. But when we take the parabola of the thermally toughened glass and the curve of the chemically toughened glass and combine them by first chemically toughening them and then heat toughening them, we maybe achieve a more positive curve. Yeah. So I will have to thank our sponsors and you too also for the kind attention, and yeah, I'm open for questions.
Thank you very much, Maximilian, for this thorough presentation. Are there questions from the audience? clear. Hello.
Hello.
So with your device, could you measure the different levels of stress through the thickness? Because when you are doing chemical tempering on the surface of the glass, you had a very nice parabola going from compression to tension, but there are actually some peaks in the compression layer on the very surface. Could you measure these very precisely?
We couldn't see them actually. I think if you really think a step forward again, you would have to improve the points where the laser can pick up its values. So if the more you get it, not discrete, the better, the higher the probability that you will measure these peaks is, I think. Yeah.
Other? I have a question.
Yeah.
You, with a sculpt, you measured through the whole thickness from surface to surface, or?
No, it's not possible with the Sculpt 0. Therefore, we had to measure from both sides. It's with the Sculpt 05, it's 2.45 millimeter maximum depth. But we then
what is then the overlap in the middle?
yes, by the 4 millimeter. No, we just started with 6 millimeters, and so they didn't overlap. With, yeah.
Okay. And you didn't have a problem. What was the scattering result? Because you show results, but the scatter within one result.
Yes. Okay. That might be still some irregularities because it depends on the composition of the glass, and if the chemical composition is maybe on the one point a little bit different than the other, the stresses also vary, but not as strong as with tempered glass, where you really can see the air jets and where it cooled down faster.
Okay, clear. Thank you very much. If no other questions, then thank you again, Maximilian.
Yeah.
Hi there. Did you like what you just saw? If you did, why don't you like the video, drop us a comment below, and share the video as well, since GPD is all about sharing. And to receive more videos in future, subscribe to this channel and don't forget to click the bell icon. Ciao!